just started, so please go.
Okay, wonderful. Well, welcome everybody. We're very happy to have Ian here to give a talk on, he's going to talk about construction of polynomial algebras related to superintegral systems. And maybe I'll just remind everyone to please mute. I will also mute in a couple seconds, mute your audio and your video. And if you have any questions, you can ask it directly in the chat box or using the raise your hand feature in the chat box. So thank you very much, Ian, for giving a talk for us, and take it away.
Okay, so thanks for the opportunity to give this talk in this series of online seminar. Okay, so one main thing that I would like to share is that over the years, there was the discovery that symmetry algebras of these superintegrable system take the form of finite dimensional Lie algebra, but more generally of finitely generated polynomial algebras. This is still not very clear what this means, because there is many ways to even write these symmetry algebra. So I will highlight that during the talk. But one interesting also aspect is that there is many higher transcendental functions, such as the fourth or the sixth Pandavae transcendent, that appear in some Hamiltonian, and they lead, for example, to cubic algebra. I would try to also point out how you can use the integral of motion and the symmetry algebra to obtain information on the spectrum, even when you don't have any knowledge on what the wave function could be. So this is something that could be different of some other approach that you need to rely on some way or another on the explicit wave function to characterize the symmetry algebra. Okay, so as a definition, an Hamiltonian system in n dimension can be of the following form. So in this can be thought of a space that can be Riemannian, conformally flat. Most of the time, there is a classification on space of constant curvatures, such as the sphere or hyperbolic space. And you can think in quantum mechanics that you will have a Laplace-Beltrami operator, and it will be integrable if it allows an integral of motion that are well defined in involution and functionally independent. This is in classical mechanics. There is this notion of functional independence. This is not the case in quantum mechanics, but there is still some analog. And for the superintegrability, you need to have an extra set of integral of motion that are also functionally independent and well defined, but they don't necessarily commute among each other or with this set of commuting integral of motion. And this would be referred as maximally superintegrable if it have k that take the value n-1. So this is the maximal set of integral of motion. In quantum mechanics, you will have quantum mechanical operators, and they will form algebraically independent set. This can be understood as there is no polynomial involving only anti-commutators, so no Jordan polynomial among the integral of motion. And there was a search that was started in the 60s by Winternitz, Smorodinsky, and they classify all the superintegrable system on two-dimensional Euclidean space with two integral that are at most quadratic. So this is the meaning of this expression xg. So you will have quadratic terms, the linear, and you can also have this function phi g. So this depends on the coordinate. And here you can rely on some previous knowledge from the 30s that the Schrödinger equation in 2 dimensions admit 4 types of coordinate in which there is can be separable, which is Cartesian, polar, elliptic, and parabolic, and these can be related to quadratic integral of motion. But for superintegrability, you will require to have 2 such integral, and then this will imply further properties such as multiseparability, exact solvability, degenerate spectrum. Exact solvability can have different meaning. It can be that you can solve the Schrödinger equation in terms of hypergeometric, sometime on type of polynomial. More recently, for example, there is this exceptional orthogonal polynomial or something involving the hypergeometric, but there is some algebraic description also that you can rewrite the Hamiltonian in terms of some maximal parabolic algebra, and this would imply that you have a flag of polynomial that is preserved. Okay, so there is 4 cases. Here I list 2 of them. You can see this is a deformation of the harmonic oscillator. So there is some singular terms. There is some constraint on the beta and gamma, depending that this is between -1/4 and 3/4, or above or below. You can have the possibility of even different self-adjoint extension from -infinity to infinity. And the other one is a deformation of the Kepler-Coulomb model. So this is a potential that depends explicitly on the angle, and they have many properties. For example, the first one can be separated in Cartesian and polar coordinate. The third one in terms of polar and parabolic type of coordinate. And since, let's say, 20 years, there was a lot of work that have been done on generalization, for example, with magnetic field, spin, on curved space, on Darboux space with Dank operator, position mass dependent system, even pseudo Hermitian model. And there is a classification that has been ongoing for model on conformally flat space. In particular, in 2 dimensions, this is complete, and there was 59 such model that can be reduced to 12 equivalence classes that can be related via Inonu-Wigner type of contraction. And there is some work that have been done by Jonathan Kress, Joshua Capel, also on classification on 3-dimensional space. This is still ongoing as well. But what can be understood from this work is that quadratic algebra play a role not only in obtaining the spectrum, but in the classification itself. And there is a connection with the full ASCII scheme of orthogonal polynomial. So even in 2 dimensions, this is quite rich structure. And to give more detail on what is the algebra, I will denote this by Q3. It has 3 generators, and this is mainly the way it flows is determined by the fact that A and B are second order polynomial. C is a third order polynomial. So it can only close up to some arbitrary structure constant alpha, gamma, delta, epsilon, zeta, A, D, and Z. And these can depend on the Hamiltonian or any other central element of the algebra. So for example, because the commutator of B and C can be at most, if you think of a differential operator realization of order 6, then a 4. So then Z can be a second order polynomial of the Hamiltonian. And this is connected in some way to other type of algebra. There is the ASCII-Wilson algebra, which contain also some cubic term. And for A equals 0, this is the now well-known Raka algebra, for which there is various generalization and connection also with something that is called the Banach-Ito algebra. So these have been studied over the years, and they have been used explicitly to get information on spectrum of quantum system, which have the superintegrability property. Okay, and something that I would like to discuss is when you go to higher order integral of motion, you can still classify the system. This has been started around 2002 by Simon Gravel and Pavel Winternitz, where they tried to obtain system on two-dimensional Euclidean space with a second and a third order integral of motion. And they discovered that this is a quite rich problem, because you will get model involving the first, the second, and the fourth Pandavae transcendent. This has been extended for when you have one second order integral and one fourth order integral of motion, where you get the first, the second, the third, the fourth, the fifth Pandavae transcendent that appear. And if you, this is in the case that you have separation of variable in Cartesian coordinate. And when you have separation of variable in polar coordinate, you get also the six Pandavae transcendent that do appear. So this is the form of the integral of motion. This can be also rewritten in various forms that can take advantage that when you look at the compatibility equation, many equations, so by compatibility equation, I mean when you take the commutator of X with the Hamiltonian H, many equations won't depend on the potential itself, and you can solve them directly. So this allows to get a system with reduced amount of equation. And I would just illustrate this by the problem with the third order integral of motion. So this is the integral B. So the leading term depends on these parameters A, I, G, A. So L3, this is the angular momentum. P1 and P2 can be think in the quantum mechanics as define I minus H bar del X1 minus I H bar del X2. And you have arbitrary function G1 and G2. You can get rid of the second order terms by, because this is Hermitian, and so there is some transformation that can be done to obtain this form. And there is some work here that has been done already, but at the end you get 4 equations and you have 3 unknowns, so G1, G2, and the potential itself, V. So this tells us, for example, that when you know the potential, this system is linear, but when you don't know the potential itself, this is a nonlinear system of equation. This is overdetermined, and you can obtain the solution. In the original paper by Gravel, there was a list of 21 quantum system and 8 classical system. And 5 of them in the quantum case can be written in terms of 2 in terms of P1, 2 in terms of P2, and 1 in terms of P4. So this is the Hamiltonian in terms of the fourth Pandavae transcendent. So as you can see, it depends on P4 square, P4, the derivative of the fourth Pandavae transcendent, and the fourth Pandavae transcendent satisfy this nonlinear second order differential equation. So something that I want to make emphasis is that when you go to a third order integral of motion, you will get these higher transcendental function that appear in the potential, which make that the usual technique, for example, Frobenius approach to get a solution of differential equation cannot be applied directly. And in some way, it would be very hard to see how to approach such problem without any knowledge of the integral of motion. So this is why these symmetry algebra are useful. This is for these cases that appear when you go beyond quadratic integral of motion, that there is no way to tell a priori what will be the wave function or the spectrum. So you try to constrain the form of the spectrum using the symmetry algebra. And this calculation have been extended, for example, on in a general way for Riemannian space, and there is some explicit calculation that have been done with Bjorn Burston, Willon Miller recently on the sphere and hyperbolic space, where you get some Hamiltonian in terms of the fifth and the sixth Pandavae transcendent. So this is a general feature of third order superintegrability that you will get these complicated model. And just to give some insight, how these work on the classification rely more or less so far on work by Cosgrove, Chazy, and Bureau on these third order differential equations that are analog of Painlevé transcendent equation. And these have a connection also with what is called second order and second degree type, Painlevé type equation. This has been classified in the 90s by Cosgrove and Skoufis. And you can rely on these work to solve these equations that appear from the overdetermined system of equation that you get by looking at commutating higher order operator with the Hamiltonian. But there is some work to do before you reach such third order equation. But once you reach that point, you can rely on these work. But this is quite remarkable that we get Painlevé transcendent for this model. And okay, also something to that can be done is to characterize the symmetry algebra. So for example, if you have a second order and nth order integral of motion, you will get such symmetry algebra where, for example, the commutator of AC involves these terms with alpha I. So you get higher power of A, and as well in the commutation relation BC. There is technique that you can rely on to study the finite dimensional representation of such deformed algebra. And such algebra also appear in other contexts. For example, Vinet and Nicolas Crampé, Zedanov in series of paper in 2019, 2020, they have obtained Oin algebra that is quartic, or for example, there is a cubic algebra that is a special case of this algebra that was referred as a Calabi-Yau algebra that is related to the missing labeling problem of SL3. So in some way, these algebra can also appear in other contexts. So it worth also looking at them from many perspectives. Here I give the case of the cubic algebra, and I want to point out that there is a unique Casimir operator that is quartic, because there is this A at the power 4 here. So this is an element in the enveloping algebra that commute with the generator A, B, and C. Again, the structure constant can depend on the Hamiltonian or any other central element of the model. The idea is to rely on deformed oscillator algebra, which is in some way of a simpler form. So the structure function phi, so phi of n, this depends on generalized number operator. You can think of B and B dagger as creation and annihilation operator, and they will act on some vacuum. And you can construct, given some constraint, Fox type representation. Generally, the structure function will depend on the Hamiltonian and also the central element. So this will provide constraint on the energy spectrum when you look for a superintegrable system. And you have a finite dimensional representation when the structure function vanish for some integer p+1. This indicates that every level have degeneracy that is p+1. Okay, so the realization of these polynomial algebra okay, so one question. So is this algebraic structure just a Lie algebra? There is some work that I was aware on these, but as far as I know, this will be different. And for the hierarchy of these polynomial algebra, you can find deform oscillator algebra realization of the following form. There is a splitting of cases depending of the parameter beta being 0 or not. You need also to ensure that some parameter delta is not 0 as well. But this structure function phi will be a polynomial. In this case, it will be a quartic polynomial, and in the other case, it will be a polynomial of degree 10. Okay, because I mentioned base structure constant can also depend on the Hamiltonian. So this expression in practice can be quite involved, but still you can manage to, once you get these expression, to solve algebraically get the spectrum by imposing the constraint on the structure function. I will illustrate by one example. So again, this example involving the fourth Pandavae transcendent. So G1 is a function of this fourth Pandavae transcendent and the derivative. There is an obvious integral because you have separation of variable in Cartesian coordinate. And there is a third order integral of the following form. So it depends on the third derivative of G1. So this will depend up to the fourth derivative of the Pandavae transcendent. But you can show that it have the following symmetry algebra. And it depends in some way. For example, the term with a square depend on the Hamiltonian here. And there is some function of the Hamiltonian itself that is cubic. So you have HQ, H, and some constant term. They depend on the parameters alpha and beta of the fourth Pandavae transcendent. And you can manage to reduce the quartic Casimir in terms of the Hamiltonian only. So this is quite involved computation, but you only rely on the differential operator realization. You don't assume a priori any knowledge on the wave function in that computation. So this is in some way algorithmic calculation. And you get the structure function. And when you do the analysis of the different cases for the finite dimensional representation, you get, in fact, there is different solution that are linear in P. So this is more or less like the harmonic oscillator, but you can have many band or many sequence of equidistant level. And it could be additional degeneracies depending if these sequence of level coincide or not. There is also the possibility of having finite chain of level with infinite dimensional one. So this is a distinctive feature for this model. And using other techniques like supersymmetric quantum mechanics, you can manage also to obtain the form of the wave function, not explicitly, but you can obtain 3-0 mode for a third order ladder operator and 3-0 mode for a third order creation operator, and you can do the analysis depending of the parameter alpha and beta of the fourth Pandavae transcendent of the different cases. So this is quite complicated, but you can show that this computation using supersymmetric quantum mechanics or Darboux or intertwining operator corroborate what you can get from the cubic algebra. So this is one example that illustrates that you can obtain in quite detail the energy spectrum for a model that you will not be able to solve using the usual method. So even if you have the separation of variable, this is not very useful, but the integral of motion can lead you to the spectrum. Okay, so this can be applied also for quartic or higher order integral of motion, or even integral of motion of arbitrary order. This has been done for model related to this exceptional orthogonal polynomial. But what I want to point out is that this method can also be applied when you, in some way, increase the rank of this polynomial algebra. And one case is a very particular one where, for example, the quadratic algebra will take the form of a Q3 algebra with some Lie algebra in a direct sum. But there is some, this is not completely separated in the sense that the structure constant of this Q3 algebra will depend on the Casimir operator of this Lie algebra. So in some way, you need to rely on the Casimir operator of the Q3 algebra, but as well on the Casimir operator and their eigenvalue of this algebra Ln. And this have been seen for various deformation of the Kepler-Coulomb system, singular theater, and even some deformation of the Kepler-Coulomb system with non-abelian monopole. So even if this is very restrictive, this is still an interesting cases to look at. But something that has been pointed out is that Q3 algebra with tree generator, even if very particular, can still be useful for, let's say, general rank quadratic algebra by using the idea of a substructure. This is not a subalgebra, but this can help to get some information on the spectrum. And I will give one example. This model has been obtained around 2001 by different authors, but no algebraic derivation of the spectrum was obtained until recently. And this is a Kepler-Coulomb system with some deformation. Here, the fact that it don't depend on the n component in this sum here is quite important because in general, this model would have second and fourth order integral of motion, but when you don't have this term, you have only second order integral of motion. So it has many properties. It can be separated in hyperspherical, hyperparabolic type of coordinate system. You can obtain the wave function in terms of hypergeometric type of polynomial, for example, the Laguerre polynomial, or you will get the Jacobi polynomial for the angles, and you can characterize the energy spectrum. But what I want to point out is that there is 2n-1 integral of motion in classical and also quantum mechanics. So this integral x can be understood as a Kepler generalization of the Runge-Lenz vector here. And there is integral ZL and YP. So they depend on the angular momentum square. And in some way, you can think of this system related to what is called the coalgebra. So if you would think of a some tensor product construction where you would use a partial Casimir, days will be in some way left and right integral of motion. So you will build using partial Casimir related to the component, and you will index from the left or the right. And this is related in some way with the Raka algebra as well, but you have an extra integral x. So in some way, this is something more general than what is referred as the Raka algebra. But there is many of these integral that commute among each other, but there is also many set of n commutating integral. And by construction, in some way, there is yi commute with yp, and the z also come. Yes? So they commute, the z commute among each other, but the z don't commute with the x. And okay, one thing to see is that you can form quadratic algebra with only 3 generators. In fact, you can form many of such substructure. They don't close among themselves. For example, if I take y1, which is one of these integral that could be interpreted from coalgebra, and this extra integral x, they commute to give you something of third order, which when you commute again, you get something that is closed in a quadratic way, but it depends on the Hamiltonian h, which is expected because this is the central element, but it depends also on Zn minus 2. But Zn minus 2 is central relative to y1 and x. So in some way, this is closed. And you can apply the construction of the Casimir operator and the deformed oscillator algebra for that substructure up to pay the price that at the end, you will get some constraint on the Hamiltonian h, but up to the eigenvalue of this operator Zn minus 2 that you don't know a priori. But there is other substructure that you can rely on. So for example, Z1 with Y2 close, and it involves other central element relative to the generator. And you can build in such way another set of n minus 2 substructure that satisfy the Q3 algebra. And all of these, they close in a quadratic way with only the generator and central element relative to that structure. So you can construct a set of n Casimir operators. So this is not Casimir of the whole algebra, but relative to each of these substructure. But in the realization, you can rewrite all these Casimir operator in terms of the central element relative to this substructure. But all these central elements form a commutating set of n integral of motion. So in some way, you can characterize the spectrum of these commutating operator n of the Hamiltonian by combining these constraints that you obtain. And you can recover the energy spectrum. So for example, P is the dimension of related to this deformed oscillator. The Ng is a set of other quantum number. They are related to this integral Z that you can characterize also explicitly. And Pi depend on the parameter beta I. So this is a explicit form for the energy spectrum. And one thing that has been observed is that this construction is quite general in some way, because these integral y, I, and zl, they are the one that you obtain in the coalgebra approach that was applied in the 2000 to get many model on curved space, on generalization of Darboux spaces. In some way, this idea can be applied to today's model to obtain their spectrum up to an extra integral that would be analog of X, because the coalgebra approach only provides you quasi-maximal superintegrability. So in some way, this shows that not only you can apply the form of theater for cubic or higher order polynomial algebra, but to higher rank quadratic algebra, even without having a knowledge of the classification of the finite dimensional representation, for example, or even an understanding of what the enveloping algebra mean for days. But something that we can do also is to look another example that have been studied quite extensively, that is the Raka algebra that is related to the generic Hamiltonian on the n-sphere. And this model is quite important because in 2 dimensions, how the superintegrable system in 2 dimensions on conformally flat space can be related to the generic model on the 2 sphere. So this is quite natural to try to look for the symmetry algebra or of the model on the n-sphere, and this has been done, for example, by Vinet, and there is some recent construction that explain that you can obtain in some way the symmetry algebra in the integral using what is called the commutant of a Lie algebra. But these approaches are more or less relying on explicit realization in terms of differential operator and the representation. I will explain in the last part of the talk that you can in some way obtain symmetry algebra in a purely algebraic way. But what I would like to also emphasize is that the Raka algebra is in fact the symmetry algebra of a wider class of superintegrable system. In fact, our model, generic model on pseudosphere, share the Raka algebra as symmetry algebra, and you can still understand this in terms of some commutant. And not all base cases on pseudosphere are interesting, because only some of them you can construct bound state if you apply solution of the Schrödinger equation using separation of variable, but still you can prove superintegrability and obtain the symmetry algebra. Okay, here I won't use a notation where you have the index above, because everything is in expressed in a way that the metric coefficient, they have the form of a diagonal matrix where you have the signature p q plus 1. And so you can think of this as a quadratic expression of the angular momentum, and in some way generalization of the angular momentum related to SO p q plus 1. And you have some deformation terms that are inverse square. And you will have additional constraint here because you want to be on this pseudosphere. And you can do the more, because you can obtain intertwining operator, and these intertwining operator, they can be explicitly constructed to act on the wave function as well, and they can more or less also be used to construct the symmetry operator, but I will give them explicitly here. So this is the QIG. You can think that there is some implicit sum here, and the form is very similar to what you can obtain on the sphere. But what is quite interesting is the form of the quadratic algebra that can be obtained very explicitly. So you have this QIG, and their commutator is the CIGK. And the only thing that happens is that this QIG depend on 2 coordinates, the CIGK on 3 coordinate. So it will depend on if on the left side there is one common or two common index, and you will get different commutator relations. So when you have, for example, QGK, CIGK, so two common index, you get this expression. But when you have only the index K that is the same, you get another expression. The H bar are here explicitly to indicate that when you take the limit in the classical case, the terms that are related to H bar square, they are present, but the one with H bar at the power 4, they disappear. Okay, and in some way, this the origin of this algebra can be seen in classical mechanics in some way. And I would just illustrate again by one example. This is in 2 dimensions. In some way, you can think of this as on the two-sphere, on the hyperbolic space. If the metric coefficient is not present explicitly, it depends on the way you define the integral of motion. This would be artificial if you would get the metric present. But you can apply, again, the deform oscillator algebra, because this has the form of a quadratic algebra like Q3. And you can obtain, again, by using the Casimir operator in terms of the Hamiltonian only, the spectra. So this is the energy here. So this is the explicit structure function. So the details are not very important, but the idea is that this is the same prescription. You apply the realization, you obtain the Casimir operator, you express in terms of the central element, and with the finite dimensional representation, you can get the spectrum. Here, the epsilon, they take care of the metric element. So if this is on the sphere, they will be all positive. If it would be on the hyperbolic space, one of them would be negative as well. Okay, so these construction, they are all relying on explicit differential operator. There is one thing that can be done is to look at this problem from another perspective. So can we understand the symmetry algebra, the Hamiltonian, the integral of motion using a Lie algebra without relying on the explicit form differential operator? There was some work by Calzada, Negro, Del Olmo in the 2000 using various Lie algebra to construct the integral of motion. This work have not been in some way using this connection to obtain the algebra, because this is not quite direct. You need to go to higher order polynomial in the enveloping algebra to get something that close. So in a recent paper with Francisco Correa, Mariano Del Olmo, and Javier Negro, we have looked again to the model that is the generic system on the two-sphere, so the S9. And you can think of X1 up to X8 to be the generator of SU3. The Cartan could be think of X1 and X2. C2 would be the quadratic Casimir operator. And you can form the commutant. So if you look for all the second order polynomial in X1 up to X8 such that they commute with the Cartan X1 and X2, you only get these three polynomial, and you can form the Hamiltonian by the sum of T1, T2, T3, or you can write in an alternative way with the second order Casimir and the Cartan. And when you use the explicit realization, you will get the usual integral of motion for the model on the two sphere. But if you take further, let's say nested commutator, so if you go to a cubic expression by taking, let's say, commutator of T1 with T2, T1 with T3, T2, T3, and you go on with T1 to 1, T1 to 2, and so on, you will get the following closed algebra. So it involves these anti-commutator here and these totally anti-symmetric three anti-commutator. But in some way, some of them can be related among each other. So but this is quite surprising that we get an algebra that don't depend explicitly on the central element. So they don't depend explicitly on x1, x2, or the quadratic or cubic Casimir of SU3. So in some way, this could be think as the symmetry algebra of the S9 model. But you can also rely on the quadratic and cubic algebra to rewrite the commutator T1, 2 with T1 and T1, 2 with T3, for example, as a quadratic expression. It's not quite quadratic because in some way C3 contain cubic element and you will get higher polynomial of the Cartan generator. So this is quadratic up to viewing the Cartan element as part of the structure constant of this algebra. And you can do more. You can calculate a Casimir operator. You can write it in terms of the generator or in terms of the central element only. So in terms of x1, x2, and the quadratic Casimir C2 and the cubic Casimir C3. So this would be algebraic characterization of the symmetry algebra. And in some way, this would reduce to the Raka algebra with constant structure constant when you insert the realization. Okay, so some concluding remark. So what I wanted to discuss is that these quadratic and polynomial algebra, they appear quite naturally as symmetry algebra of superintegrable system. There is this connection also with Day's model with Painlevé transcendent. So all the Painlevé transcendent do appear in Day's superintegrable system. But also that most of these approach, they rely on explicit realization, but you can also characterize the symmetry algebra by using enveloping algebra of Lie algebras. So in some way, there is some close connection with something that have been looked in the 80s and 90s, which are the massas, so the maximal abelian subalgebra. And so this could be used as well to look at some of these superintegrable system from another point of view. Something that can be looked at is at various models with coalgebra that generalize, and in fact, you obtain symmetry algebra that embed the Raka algebra in some more general structure that you can still use to obtain information on the spectrum. And some other work, for example, with Sarah Post and her PhD student, Lisa Reiter, for this model involving the 6 Painlevé transcendent that so far has not been solved in a general way, but we have been able to look at some particular cases that satisfy some cubic algebra that are connected with Jacobi exceptional orthogonal polynomial, and we were able to obtain the spectrum as well algebraically. Okay, so thanks.
Thank you very much, Jan.
Yes.
Okay.
I have a question.
Okay.
Can you go back to the page where you were talking about the Hamiltonians involving Pandavae transcendence? You had examples with Pandavae 4, for example.
Yes.
Right. So these Pandavae 4 transcendence, they depend on Z, I guess. Oh,
yeah.
no, they depend on X. In the Hamiltonian, they depend on X. And what I wanted to clarify is, which is the time variable for the Hamiltonian? It's not X because that's one of the coordinates, right?
Here Z is in fact X with the square root of omega
Sure.
H bar. Okay,
But the Hamiltonian system itself, does it depend on, I guess we're talking about, I'm a little confused about what the independent variable of the Hamiltonian system is.
this is time independent and Hamiltonian.
So it's autonomous.
But recently with Véronique Hussin and Kevin Zelaya, we extended in fact this Hamiltonian to time-dependent setting. There is a way, but here there is something that would be different, is that you will not have, in fact, you will have some conserved quantity that you can rely on to get the eigenvalue, and that you can then map to your time-dependent problem. But this is non-trivial to do this connection, but you can obtain time-dependent model, but you need to rely mainly on this Darboux transformation to make the connection with the time-dependent system. And you can still obtain the wave function or even characterize in some way the eigenvalue of some conserved operator related to the time-dependent Hamiltonian.
Okay, thank you.
Any other questions? Maybe, I think you mentioned it, and maybe I'll bring you back to the question of, I think it was George who asked whether or not these quadratic algebras are related to like the Lie 3 algebras or other general, other connections to other algebraic structures.
There could be relation as well with, for some cases, the W algebra and other algebraic structure. I think this is not yet clear, I think in general, what are these connections, but there should be some connection for some particular example. For example, the anisotropic harmonic oscillator in 2 dimensions, with frequency 3.1, I think it can be related to the W, to some W algebra for that example. I've seen some explicit calculation. So there could be some relation among these algebraic structure. But one thing that is, because there is some freedom as well. So if I go back to this Raka algebra, there is some, these QIG are not necessarily the set of functionally independent integral. There is some relation among them. And for example, there is even a linear relation. For example, the sum of the QIG is related to the Hamiltonian. So there is some freedom to even rewrite the symmetry algebra by using some other constraint, because these algebra have been constructed using explicit differential operator, and there is further constraint in the enveloping algebra. For example, here, like the QIG, the anti-commutator of the CIGK with, let's say, CIGL close as well. And there is some quadratic relation among the QIG. And I think that there is further constraint in the, let's say, the enveloping algebra as well. So what is really the symmetry algebra? I think that there is some ambiguity as well.
Great, that makes sense. Great. And I think George has also asked if we're talking, if your GIJ is your Riemannian metric, or you have, or is it a symplectic form? Symplectic metric?
So the GIG, they are only the analog of angular momentum, let's say, on the pseudosphere. So the GIG are this diagonal metric with the signature between being related to P Q plus 1. So it's more or less the angular momentum, but with some plus and minus for some of them. But what is quite surprising is that it don't depend explicitly on the metric. So the Raka algebra is a symmetry algebra of this world of model. Let's see the chat. So this is always in because here we are related to pseudo sphere. So this is not quite Riemannian metric here. So you can have some other type of space where, for example, you don't have even bounds that can be different. So this is quite general, and not all of them are necessarily interesting from a, like, let's say, physical perspective.
Okay, I think we're getting close to time, but does anyone else have any last questions that you wanted to ask?
So if there is no other question, I can make the announcement for the next talk, which will be by Professor Milena Radnovich on the 18th of August, same time, whichever is your time zone. And she will talk about the integrable billiard and extremal polynomials. And I would like to thank all the people that participated today, and of course Ian, who gave a very nice talk. So I think I'll stop now the recording.